Welcome to the debate. Imagine trying to fix a massive traffic jam right in the center of a bustling city.
Okay, sounds stressful.
Right? And in our current reality, you really only have one option. You optimize what's already there. So you change the timing of the red lights, you reroute cars through existing avenues, and you just sort of hope the grid can handle it.
Yeah, you're stuck with the roads you have.
Exactly. But imagine if instead of just tweaking the traffic lights, the city instantly paved a brand new high-speed highway straight from the traffic jam to everyone's destination. And then, and this is the crazy part, it dissolved that highway the moment the cars arrived.
Wow, I mean, that would be magic.
It would, but that dynamic, impossible city is actually exactly what your brain is doing right now. And today we are diving into Guy Lakeman's really provocative theoretical framework outlined in The Biological Architecture of Machine Intelligence.
Such a fascinating read, honestly.
It really is. Lakeman posits this fundamental distinction that, frankly, challenges everything about how we are currently building AI. He argues that intelligence is a well-defined process with measurable metrics. It is not merely an artificial replication of an item.
Right, like building a prosthetic arm.
Exactly.
And that distinction between replicating a physical item and replicating a conceptual process is really the crucible of our entire discussion today. I mean, you don't need a bird's physical feathers to build an airplane, right? You just need to replicate the process of aerodynamics.
But that is exactly where the tension lies in Lakeman's work. Because the central question we are unpacking today is this. To achieve true machine intelligence, an intelligence that can actually scale all the way up to superintelligence, must we strictly replicate the biological neurons' dynamic physical search and connect mechanisms? Or can we do it another way? I will be arguing that the static nature of current large language models, or LLMs, is a fundamental limitation. I believe true intermodal intelligence actually requires replicating the agile searching nature of biological axons and, alongside their incredibly efficient analog energy consumption. To master the process, we absolutely have to mirror the biology.
And I approach this from an entirely different angle. I will be arguing that while biology undoubtedly offers one highly efficient method for the process of intelligence, binding machine intelligence strictly to biological mechanisms, like demanding a system physically search for a connection, is an unnecessarily restrictive framework.
Okay, but how else do you achieve it?
Well, I believe the process of intelligence can be fully, robustly, and mathematically realized within the static, predefined matrix structures of our modern artificial neural networks. We don't need the biology to get the result.
Let's lay out our positions clearly here by looking at the reality of what biology actually does versus what our current algorithms, pretend to do. In the pursuit of AI, we've taken the physical item of the human neuron and replicated it strictly as a digital algorithm.
Yeah, the digital neuron.
Right. But in doing so, we have fundamentally ignored the physical dynamism of biology. I mean, biological neurons possess agile axon terminals. These aren't static wires soldered onto a motherboard.
No, they're living cells.
Exactly. They are living things that actively squirm and search the dendrites of other neurons they want to connect to. Current artificial networks are stuck in predefined matrix algorithms. Learning in an LLM is exclusively associated with weight construction.
Changing the traffic lights in your city analogy.
You got it. There is no structural adaptation at all. Replicating the neuron's physical connection mechanism is a huge leap, obviously, but it's necessary. A fixed grid will never achieve the fluid, intermodal inference that characterizes true expanding intelligence.
It's a compelling argument, but have you considered that a process can be perfectly and successfully replicated without mimicking the original item down to its physical quirks?
I mean, I have, but I don't think it works here.
Well, look at predefined structures using backpropagation, which for the audience is essentially just a mathematical way of measuring how wrong an answer is and working backwards to adjust the weights of the connections. That can functionally replicate the intelligence process.
Functionally, sure, for narrow tasks.
But I am deeply skeptical of the premise that an artificial neuron must physically or structurally grow to qualify as an expanding intelligence. Mathematical weight adjustments in a sufficiently large matrix simulate the exact same intermodal inference.
Wait, let me stop you there because we just threw out intermodal inference, and we should probably unpack that for a second.
Good point.
By intermodal inference, we're basically talking about the brain's ability to connect entirely different types of information instantly, right? Like linking the smell of smoke to the visual concept of fire, or applying a mathematical concept to a musical rhythm.
Precisely. It is the ability to infer relationships across totally different modes of data. And my stance is that if I have a digital matrix connecting every conceptual node to every other node, and I adjust a mathematical weight between them from 0 to 1, I have functionally created that exact same intermodal connection.
Okay, but you're just simulating it.
But the math does the heavy lifting. I don't need a biological style structural routing mechanism to achieve that synthesis.
I see why you think that, but let me give you a different perspective. And it starts with a hard physical limit that makes your massive mathematical matrix incredibly problematic, and that is energy.
Ah, yes. The energy problem.
The leap to replicate the dynamic biological neuron isn't just a fun thought experiment, you know. It is a desperate necessity tied to power consumption. Lakeman outlines this beautifully. He points out that a digital bit of information requires significantly more energy than a biological multiple-level analog system.
The energy disparity is well documented, yes. But I think we need to look at why that is.
Right. So let's explain the why behind that disparity. In a digital system, everything is binary. To represent complex data, like the nuance of a specific color or a complex thought, you need massive strings of ones and zeros.
Millions of them.
Millions. You need multiple bytes just to represent one piece of nuanced data. But in an analog biological system, a specific chemical gradient or a voltage level just is that state. It doesn't need to be broken down into millions of binary flips.
Because analog information requires fewer bits overall.
Exactly. And the exact figures Lakeman provides for the digital side are just staggering. To erase a single digital bit of information requires 2.9 times 10 to the negative 21 joules.
Right, that is Landauer's principle in action. The strict physical limit of thermodynamic cost for erasing data.
Yep. It's 0.018 electron volts per bit. Now, that number might sound tiny to someone listening, but multiply it by the trillions of calculations an LLM does every single second. For a digital neuron, raising or lowering a binary bit requires vastly more energy than its biological analog equivalent.
The scale is definitely massive.
We are essentially powering a small city to run a large language model. Meanwhile, the human brain does vastly more complex routing on roughly 20 watts of power, literally less energy than a dim light bulb.
It is incredibly efficient.
That's the real aha moment for me. You know, biology's analog system runs on a bowl of oatmeal. Our digital matrices require a dedicated power plant. Plus, biological neurons don't constantly replicate data, which keeps their baseline energy use exceptionally low. We are trying to build superintelligence on a digital framework that is inherently energy ravenous.
I mean, I don't dispute the thermodynamic realities at all. Erasing digital bits generates heat and costs energy. Landauer's principle is an inescapable law of physics.
Right?
But I have to ask you a philosophical question based on the material here. Is this energy disparity a fatal, theoretical flaw for digital machine intelligence, or is it merely an engineering hurdle?
A fatal flaw, I'd say.
Well, let me put it to you directly. If we had infinite energy, say we had Dyson spheres harvesting the total output of a star to power our server farms, would the digital binary approach still be fundamentally intellectually inferior to the biological approach, or is your argument here purely about resource constraints on Earth?
That's a really fascinating hypothetical. Though, I would frame the reality differently. It is not just about the power bill at the end of the month.
Okay, then what is it about?
The energy architecture fundamentally dictates the processing architecture. because digital requires so much energy and so many binary bits to represent complex states. It actually forces us into these rigid, predefined matrices just to make the computation manageable.
Because doing it dynamically is too expensive.
Yes. We have to build the city grid because the math of doing it dynamically and binary is just too chaotic. Biology's analog efficiency is exactly what allows it to maintain those dynamic searching axon terminals.
But the matrix is highly organized. I mean, it's a very elegant structure.
Organized, yes, but painfully limited. Let's look at how the connection actually works in biology compared to the LLM. In biology, a sensory receptor cell, say for light, pressure, temperature, transmits raw data to a neuron dendrite. That neuron then retransmits via its axon to other neurons in a chain.
Right, and it transfers that information through the weight determined in the connection synapses, which again is exactly what our matrix algorithms replicate. We multiply the input by a weight, which simulates the synaptic strength.
But that is only half the story. This is where Lakeman makes a totally critical distinction. Yes, biology can transfer information through a weighted synapse, filtering the signal. But it can also transfer information through a direct presynaptic connection without any weighting filter at all.
Bypassing the filter.
Exactly. It just passes the raw signal straight through. Current LLMs completely lack this ability. Every single impulse in an artificial network must pass through a weighting filter. They cannot dynamically search for new output connections, and they cannot bypass their own weights.
So you're saying,
if an artificial network cannot bypass its own weighting filters via direct presynaptic connections, aren't we fundamentally capping its ability to process raw, unfiltered sensory input?
I'm sorry, but I just don't buy that. Let me tell you why. Because I think you are conflating the physical routing of a signal with its mathematical representation. Let's really break this down.
Go ahead.
If an artificial network needs to pass raw, unfiltered data from node A to node B without altering it, the matrix algorithm simply assigns a mathematical weight of exactly 1.0 to that connection.
And a weight of 0 to all interfering connections.
Wait, I want to clarify that so we don't lose anyone in the math. You're saying if we just assign a weight of 1.0, it's functionally the exact same as a biological axon making a direct connection?
Yeah, because multiplying anything by 1 leaves it exactly the same.
Right.
Precisely. In linear algebra, this is basically an identity matrix. It perfectly preserves the raw input. Conceptually, we really have to separate the mechanism from the outcome here. In biology, the mechanism is a physical axon, literally bypassing a chemical filter to drop a raw signal.
And the outcome is the unweighted impulse.
Exactly. Now, in an LLM, the mechanism is multiplying the input by 1.0. The outcome is the exact same, the transmission of an unweighted impulse. An LLM receives inputs, processes them through these mathematical weights, and transmits outputs perfectly well without needing a physical axon squirming around looking for a dendrite. The math simulates the structure perfectly.
Well, I'm not convinced by that line of reasoning because mathematically simulating a connection is not the same as physically building one.
How is it different if the result is the same?
Because the length of 1.0 is still a fixed pathway in a predefined grid. It is still a traffic light that just happens to be permanently green. And that green light costs computational energy to maintain, to check, and to process, even if it's just multiplying by 1.
It's a minimal cost, though.
But it adds up. It is not the same as the network actively recognizing a novel stimulus and growing a new connection to an entirely different part of the brain that previously had no structural relationship to that input.
But if the grid is large enough...
But the grid can't be infinitely large. The artificial neurons of an LLM do not dynamically search for or create new connections. Their learning is exclusively associated with weight construction on roads that someone else already built.
That is true. They operate on existing infrastructure.
Right. So if those fixed pathways in an LLM are permanently green lit, how does the system ever learn something fundamentally new without exploding its energy budget by adding billions of new permanent roads? And, that brings us exactly to Lakeman's proposed solution, which attempts to break AI out of this fixed matrix.
You are talking about his concept of integrating internet search functions into the neural network architecture?
Right. Lakeman proposes this fascinating method to expand the LLM system. He suggests using live internet search and find functions to create a network of what he calls analytic neurons.
It's definitely an outside-the-box idea.
It is. Now, what does that mean? These analytic neurons essentially implement the digital equivalent of biological axon terminals. By actively searching the internet, they are finding responsive nodes. Think of them as digital acceptance dendrites attached to the broader external network of human knowledge.
It's a very aggressive claim on his part.
But an elegant one. This auto search and connect mechanism adds vastly more processing power to the standard backpropagation learning process. It isn't just adjusting weights on existing roads. It is dynamically hunting for new relevant nodes of information entirely outside its original programming.
Which he compares to an axon search.
Yes. This process of axon searching is exactly how connections within the biological brain expand those intermodal intelligence metrics. According to Lakeman, this specific dynamic search function is how a limited general intelligence actually leaks to become a superintelligent know-all.
Okay, but I want to apply some rigorous scrutiny to this specific framework because I think we really need to unpack how this actually works under the hood. Lakeman's proposal to map an internet search query directly to a biological axon search feels like a deeply flawed metaphor to me.
How so? It seems pretty parallel.
Well, let's break down the actual mechanism here. I understand what Lakeman is proposing using a search engine to fetch data, but how does fetching a Wikipedia article mechanically replicate an axon physically rewiring a neural pathway?
I think the mechanism is actually quite parallel in function.
Is it though, when an LLM executes an internet search, it is sending a text query, essentially an API call to a centralized external index and retrieving text back? Are we really prepared to say that routing data through a Google search truly mirrors the internal organic spreading of modal inference?
I mean, if it brings back new concepts.
But one is structural architecture and the other is just data retrieval. An axon search in biology is an internal structural adaptation based on incredibly localized chemical gradients and electrical signals. An API call to a web browser is just fetching data.
I think
It feels like we are just bolting a massive static external database onto an already structurally static LLM and calling it dynamic.
I hear you, but I think you're underestimating the architectural shift this creates. Think of a standard LLM like a massive closed-off library. It only knows the books it has inside.
Sure.
Learning, in the traditional LLM sense, is just cross-referencing the books it already owns. But an analytic neuron doing an auto search is like a librarian physically walking out the front door, finding a brand new book from a different library across the world, bringing it back, and instantly building a new temporary wing of the library to house it and connect it to everything else.
But the library didn't grow a new wing. It just brought a book into the reading room.
Functionally, for the duration of that inference, it did build a new wing. If the definition of an axon search is simply a mechanism to find a responsive node to transfer information, why does it fundamentally matter if that search happens via a chemical gradient in the physical brain or via an algorithmic search across the internet?
Because the architecture dictates the capability.
But the process is what matters. The analytic neuron is looking for a connection that literally didn't exist a millisecond ago. When it finds the right data on the internet, it forms a dynamic connection to that external node, pulls the data into its backpropagation process, and enhances its learning. That is dynamic routing. That is escaping the predefined matrix.
It matters profoundly because of the architecture of inference, though. An agile axon terminal in biology grows toward a specific dendrite because of a holistic, system-wide feedback loop.
Meaning,
we talked about how biological systems sense light, temperature, pressure, chemical states, all operating on that highly efficient analog foundation. It is a completely integrated native system. When an LLM searches the internet, it is relying on an external, entirely different digital architecture to do the sorting and finding.
so you think outsourcing is the problem?
Exactly. It is outsourcing the search process. I would argue that matrix algorithms, as they scale, will eventually internalize all necessary data relationships. The network structure may be predefined, but if the matrix is large enough, the search happens instantaneously through internal mathematics, not through structural growth or external web queries.
But scaling the matrix internally brings us right back to the very wall we hit in segment 1, the energy barrier.
Well, energy is always the constraint.
But it's an insurmountable one here. To have a predefined matrix large enough to contain every possible necessary connection to mathematically simulate an infinite number of potential dynamic links internally, you run into a computational and energy wall that is insurmountable on Earth.
I see where you're going.
You'd be spending that 2.9 times 10 to the negative 21 joules billions of times over just to erase the bits for the connections you aren't currently using.
Right, the computational cost of zero weights.
Exactly. Maintaining billions of zero-weight connections just in case you need them is incredibly wasteful.
By implementing Lakeman's analytic neurons that utilize auto-search and connect capabilities, the machine intelligence doesn't need to maintain a mathematically infinite energy-draining matrix.
It only builds it when it needs it.
Yes, it only builds the connection to the external internet when the cognitive process demands it. That brilliantly mimics the low-energy, highly targeted approach of the biological system. It paves the road only when a car needs to drive on it. Look, I will certainly concede that the energy efficiency of biological, analog, non-replicating cells is an absolute marvel. As you noted earlier, the brain running on 20 watts is the ultimate low-energy processor.
It really is.
But we must be careful not to conflate the physical mechanism of the brain with the mathematical process of intelligence. Replicating the neuron's physical quirks like structural searching might not be the only rigorous path to superintelligence. Matrix algorithms and mathematical weight construction, while undeniably power-hungry, do successfully replicate the processing activity of receiving an input, weighting it, and transmitting an output. The process works.
It works for bounded problems, sure. Yet, as Lakeman's text clearly argues, the conclusion is that the development of a true, limitless machine intelligence requires artificial neurons that have intelligent search and connect capabilities.
You think static weights just aren't enough?
Static weights are just the beginning, emulating the biological architecture, specifically the low-energy analog processing, and the dynamic, searching nature of agile axon terminals is the only rigorous path to expanding intermodal intelligence metrics toward a superintelligence know-all.
And my perspective remains that while the hardware and thermodynamic constraints are very, very real, binding the abstract process of intelligence to the biological item's specific behaviors risks limiting our conceptual horizons.
How so?
Mathematics is universal. Matrix processing may achieve the exact same intelligence process, and perhaps even forms of alien intelligence we haven't even conceived of yet, without needing literal structural replication of human biology.
Well, I think where we do find a powerful convergence today is precisely on the limitations of where we currently stand. We both acknowledge, drawing directly from Lakeman's material, that current LLMs are undeniably constrained by their predefined structures and their massive energy requirements compared to biological brains.
Oh, 100%.
The power plant versus the bowl of oatmeal is a reality we just can't ignore.
Absolutely. We are clearly in thoughtful tension over whether Lakeman's analytic neurons utilizing internet search truly solve this architectural deficit, or if they're just, a clever software patch on a fundamentally different kind of system.
Right.
But there is no denying that the digital bit is incredibly expensive compared to the biological analog, and that limitation will dictate the future of the field.
It is a profound complexity to reflect on. We are trying to synthetically replicate a system that simultaneously senses temperature, pressure, and chemical changes, all while dynamically rewiring its own physical architecture in real time. And again, without drawing more power than a dim light bulb.
It's humbling, really.
It is. The source material leaves plenty of room for deeper exploration into how backpropagation might evolve with these auto search capabilities, or if we need a fundamentally new hardware paradigm entirely.
The search for the optimal architecture continues, as Lakeman rightly points out. There is just so much more to explore in how these systems learn.
There is indeed. We leave you to consider, when we finally build a true machine intelligence, will it be an endlessly optimized, rigid grid of traffic lights, or a living landscape constantly paving its own way forward? Thank you for listening.